Hey y'all. So we're going to start looking at a new function today. It's called a rational function. So we've been studying all different types of functions so far this semester. This is going to be the new one that we're going to be working on for the next few days. So today we're going to take a look at what the graph looks like in Desmos, talk about the domain and the range, and then talk about what an asymptote is and how to find it. So rational functions and their graphs. So a rational expression is the quotient of two polynomials. A rational function is a function defined by a rational expression. So this f of x equals 1 over x. That is our basic rational function. So a rational function, think fraction form. I'm going to have a top and I'm going to have a bottom. So this is my most basic parent function, and this is a rational function. So functions pass the vertical line test, as we know. So when we take a look at this in Desmos, it's going to pass the vertical line test. So let's go ahead and look into what it looks like on Desmos. So I've already graphed it here. So let's make this bigger for us. So this is what a rational function looks like. So you very well may want to jot this down in your notes. So it's the first one that we see here that's highlighted in a red. This is what a rational function looks like. It'll have different branches. So I have a branch that's here in the first quadrant, and then I have a branch that's here in the third quadrant. This is the most basic rational function. So it has this general shape, and it looks just like this. I want to quickly go through the transformations to show you that our transformations that we study with the other functions apply to this type of function as well. So if this is my parent function, notice what's going to happen when I incorporate graph number 2, the one in the blue. So notice here I am. This was the red function. That's our basic function that I'm going to keep in Desmos. And notice what happens when I add the blue to it. This is a reflection over the x-axis, and I'm sure, hopefully, maybe you remember that. So for this one here, if you add a negative in the front of any type of function, today we're studying rationals, but in front of any type of function, it's going to reflect over the x-axis. So the blue is a reflection over the x-axis. Now, let me get rid of this one. Let's go see what else happens. So the red is the basic one that we're looking at. Let me incorporate graph number 3. Graph number 3 moved left 2 units. So you can imagine, maybe if you want to think there's like a point right here where my pointer is, we moved over 2 spaces to the left. So the whole function shifted left 2 spaces. If I bring in a new one, let's take a look at the purple one. So if I compare the red to the purple, so this time I'm looking at the purple, let me highlight that. If we compare the red to the purple, it moved right 3 spaces. These are the same transformations that we've been studying all semester. So the one in the green that I'm going to highlight is the opposite of what you think. It moved left 2 spaces. This one here moves right 3 spaces. So the number in the problem tells you how it's going to move left or right, up or down, etc. Now let's make it move up or down. So let's take a look at this one. So look at the black one that was just added to our page here. So from the red to the black, that function moved up 5 spaces. So here we are here, what I just highlighted. This plus 5 on the outside moves the whole function up 5 spaces. Now let's make it move down. Notice that's that red one there. So it is 2 different red ones because Desmos ran out of colors. But the one that I just added there, it moved down 3 spaces. So this here that I'm moving along, that's my parent function. And then this function here moved down 3 spaces. So it moved down 3 spaces. And the last one that I want to quickly go over just to make sure you're good. If you add a number in the front, in this case, it's going to end up in the numerator. Notice what's going to happen for my parent function, which is this one right here in the red. Notice to the blue. This is a vertical stretch by a factor of 3. So let me highlight this one. This is a vertical stretch by a factor of 3. So the whole rational function, think rubber band, you're stretching it out, is a vertical stretch by a factor of 3. These transformations are all the same that we've been studying for every type of function. So if I go through that again for you, this first one here is a reflection over the x-axis if you add a negative. Next, moves left 2 spaces in the denominator. Next one moves right 3 spaces in the denominator. If you have a number on the outside, it moves up 5 spaces. This one here moved down 3 spaces. And this one here is a vertical stretch by a factor of 3. So you're more than welcome to keep your parent function in there as you're working, so that you can see your transformations if you're not quite to the point where you're picking up on the pattern. So anyway, this is our basic parent function. This is what a rational function looks like. Now I want to introduce a new word to you, and then I'll show you how to find it in your graph. So let me get rid of that for just a second. So the new word for today, I want you to write down asymptote. So the new word for today is asymptote. And don't worry about that bottom part just yet. I just want to talk to you about what an asymptote is. So this word here, asymptote, is a line a graph approaches but never touches. So an asymptote is a line your graph approaches but it never touches. So I'm going to look at the graph to kind of describe that to you. So again, that word is asymptote. It's a line a graph approaches but never touches. So if I come over here and look at Desmos, let's look at my parent function. The domain and range is not all real numbers. There's actually a number that is excluded from my domain and my range. So let me try to draw a line here. So this is an asymptote, this blue line that I'm trying to keep nice and straight for you, which is actually the y-axis. My graph gets closer and closer to this line, but it'll never touch this vertical line. So if I follow along, notice this red is getting closer and closer and closer and closer to the y-axis. It's going to look like it's going to touch it, but it's not going to touch it. There's an asymptote there. So think like a wall. So it's a wall that is going to get closer and closer to, but it's never going to touch. And there's another asymptote here. So, and that is very crooked, but that's supposed to be the x-axis there. So there's also another asymptote at the x-axis. So the red is going to get closer and closer and closer and closer and closer to this line, but it's never going to touch the line. So there are 2 asymptotes for this function. The first asymptote is the x-axis, and the second one is the y-axis. So if I ask you to find the domain and the range, which we are going to go through in just a minute, the domain for my parent function is all numbers except 0. So it's everything except 0. And our range is the exact same thing. It's all numbers except the number 0, because there's this idea of an asymptote that's there. So it's going to get closer and closer to it, but it's never going to touch. So I want to jump into some problems, how to find your domain and range given the graph. So we're going to take a look at 2 examples, and we're going to go through and we're going to find the domain and, not the range, excuse me, we're just going to find the domain for these 2 functions. So we're going to figure out what can x be. So if you're looking to find your domain, you set your denominator equal to 0 and you solve your equation. So my denominator for this first one is x squared plus 9x plus 20. To find what your domain is, take your denominator and set it equal to 0. So I'm writing in colored pencil here. Hopefully I don't mess up. But I'm going to take the denominator and I'm going to set it equal to 0. So x squared plus 9x plus 20 equals 0. We got lots of different ways I can solve this problem. I'm going to solve it by factoring because I think that's the easiest approach to get to. So we're going to solve it by factoring. So we're looking for 2 numbers that multiply to give me 20 and add to give me 9. So those numbers are 5 and 4. Okay. We know that we need to take our factors and set them equal to 0. So x plus 5 equals 0 and x plus 4 equals 0. Subtract 5 from both sides, we get negative 5. And subtract 4 from both sides, we get negative 4. So how does this help us with our domain? Our domain is all numbers except negative 5 and negative 4. So it's going to be all real numbers except negative 5 and negative 4. So it includes the set of numbers except the number 5. That's why I have to slash through it. So it does not include negative 5 and it does not include negative 4. So in a couple of minutes, I will graph this in Desmos so you can kind of get a visual that there's going to be a vertical line. That line's going to be negative 5. And then there's going to be another vertical line at negative 4. So it's going to get closer and closer to those lines, but there's an asymptote there. All right, let's try number 2. So we're going to go through and we're going to find the domain for number 2. Again, set your denominator equal to 0 and solve the equation. So x squared plus 2x minus 3. Now I'm going to factor this. You can try another way if you want to complete the square, quadratic formula, etc., etc. I just think it's probably fastest and easiest if we just go ahead and set up our parentheses and factor. So we're looking for two numbers that multiply to give me -3, add to give us 2. So those numbers are +3 and -1. We set each of these factors equal to 0, and we should get -3 and +1. So our domain is going to be the set of all numbers except these two numbers. So all real numbers, not -3 and not +1. So our domain is all numbers that we possibly can think of except for these two numbers, -3 and +1. And the reason for that is because there's an asymptote here when we look at the graph. Now I'm going to try to simultaneously put this here and put my Desmos graph there so you can see what I'm talking about as far as there being an asymptote there. So let me slide this over a little bit. Okay, so let me get rid of our parent function. I'll just keep it there and highlight this one. So this is what this function looks like. This is the first one, x squared minus 7x plus 12 divided by x squared plus 9x plus 20. So there are two vertical asymptotes. There's one at x equals -5, and there's one at x equals -4. So what that means is there's going to be some lines that I'm going to draw in here so that you can see more of what I am talking about. So this is where x is -5. So this is where x is -5. And my other line is x -4. Now these are vertical asymptotes. So vertical places where it's getting closer and closer to, and part of my cricket line there, I was drawing the best I could there. So if I zoom in a little bit there so we can see the whole parabola. Okay, and let me go the other direction there. All right. Get rid of this. Thank you so much for bearing with me here. So let's try again. So -5 is somewhere in here. And imagine that is super straight. Suppose I had a ruler and I wasn't trying to draw on the computer. And then there's another line in here. So these lines go on forever. Notice your rational function is getting closer and closer to these two lines. So my domain on the left-hand side where my smartboard is here, x is not equal to -5 and x is not equal to 4. So the green is my function. It's getting closer and closer and closer to that purple line that I drew in, but it's never going to touch it. And the same thing with the -5. It's getting closer and closer and closer to the purple line, but it's not going to touch. There's an asymptote there, particularly there's vertical asymptotes there that my line is going to get closer to, but not going to touch. All right, let us try the second one, and then maybe we'll be, maybe I'll do a little better job here with this one. So let me get rid of this. So this is the second one, and let me highlight this one. So this one, we had all real numbers except -3 and except +1. So let me try to draw in -3 and +1. So -3, 1, 2 is going to be here. So I have a line in here that my graph is going to get closer and closer to, but it's never going to touch. Okay, so I did much better with that one. And then there's one at +1. So I can draw in a line here that my graph is going to get closer and closer to, but it's never going to touch. So that's why my domain includes every number that we possibly can think of, except for those two numbers that we took out. So for this particular example, my graph will never cross at -3. It'll never get to -3, and it'll never get to +1 because we have vertical asymptotes that my graph is going to get closer and closer to. Now, I just want to end, and we've kind of already touched on it a little bit. I want to end with finding our vertical asymptotes, which are super, super similar to what we just did by finding the domain. So I just want to do these last two problems, and then we'll take a look at the graphs. So find the vertical asymptotes and state the domain. When you find your vertical asymptotes, they are exactly the same as what we just did to find the domain. So you're going to take your domain, and you're going to set it equal to 0. So x plus 4 equals 0. Set it equal to 0. Solve it. Subtract 4 from both sides. We got x equals -4. So this means that we have a vertical asymptote, and I am abbreviating here. We have a vertical asymptote at -4. And that also tells us that my domain is all real numbers except the number -4. So I got a vertical asymptote, meaning there's going to be a vertical line that my rational function is going to get closer and closer and closer and closer to, but never touch. And that means my domain is all x's in the world except -4. And the last one, same thing. Take your denominator and set it equal to 0. So x squared minus 1 equals 0. We need to solve this equation, add 1 to both sides, and take the square root, and we get plus or minus 1. So I have two vertical asymptotes for this problem. One of them is at 1, and the other is at -1. So these are my two vertical asymptotes. And my domain is all real numbers except these two numbers. So to find your domain and vertical asymptotes, you approach those the same way. Take your denominator and you set it equal to 0. And if I come over here to decimals, just so we can have a graph reference to look at. So let me get rid of this here. Okay. And shrink this over just a little bit so we can see everything all at once. So let's start with the A. So the one that says x squared minus x minus 6. So let's take a look at that one. So x squared minus x minus 6 had a vertical asymptote at x equals -4. So that means there's a vertical line at -4. So here is my vertical line at -4. So this rational function is going to get closer and closer and closer. So the black grayish color here, my rational function is going to get closer and closer to that line, but it's never going to touch. So I have a vertical asymptote at -4, and our domain was everything except -4. And last but not least, let's take a look at the very last one so we can make some comparisons to our graph and what we found. So for this one, we found two asymptotes. Over here in my green colored pencil, we found two asymptotes. One is at 1 and one was at -1. So if I draw those in, I have an asymptote here. This is at -1. And it does look like it's going to touch, but I assure you it's just going to get closer and closer and closer to that. So this is all one line. And then my other asymptote is at +1. So think it's like a wall. So the red rational function is going to get closer and closer and closer to this bluish line that I drew in there, but it's never going to touch that line because it's an asymptote. So those numbers will not be included in our domain.